4 kilograms of a certain gas is contained within a piston cylinder assembly. The gas undergoes a process for which the pressure-volume relationship is given by this. PV to the 1.5 is a constant. Initial pressure is 3 bar, initial volume is zero point 0.1, and the final volume is zero point 0.2. A change in a specific internal energies were given with this one. Delta U is equal to negative 4.6. Essentially, nag-decrease yung internal energy ng system mo. There are no significant changes in kinetic or potential. Determine the net heat transfer for the process. Okay? So let me just draw first or put first the sketch of the problem. Okay. Essentially here we have a gas in a piston cylinder assembly, and the gas is expanding, right? And we know V1 to be zero point 0.1 m cubed. Okay, P1, the initial pressure is 3 bar. Okay, and it will expand to a what? To a volume of zero point 0.2. We know V2. After the expansion, the volume now becomes zero point 0.2 m cubed, but we don't know P2. We don't have any idea of that. And this is what we know also, that the U2 minus U1, or actual delta U in this case, the change in internal energy is negative 4.6 kilojoule per kilogram. Okay, so, and the mass we are given at 4 kilograms. But the idea here is, well, to solve for this, we are looking for the net heat transfer of the process, meaning heat involved. As you can see, as the gas expands, what do you think? Is heat being added or heat being released by the gas? That's what we don't know yet as of the moment. We know that just the what? The internal energy decreases, which means that the gas essentially cools down. Well, because for most of gases, as the internal energy decreases, the temperature also decreases, because mostly for all gases, internal energy is only a function of temperature. But anyway, for this closed system, we can always use the, and this is not non-accelerating, right? We can always use this general equation, delta U is equal to Q plus W. And essentially here, if we're looking for Q, right? So Q will just be equal to delta U, change in internal energy, minus W. So I think change in internal energy is not that difficult to calculate, right? Because delta U here, we're given that it's what, 4.6 kilojoule per kilogram. Therefore, in terms of this is no a specific, meaning per kilogram. If we're looking for the actual delta U, we'll just multiply for 4 kilograms, right? We'll then be having here delta U will just be equal to, well, delta U actual, we'll put that in capital, will just be 4 kilograms times negative 4.6 kilojoule per kilogram, right? So therefore that will just be equal to 4.6 times 4, that will be 18.4. So negative 18.4 kilojoule per kilogram yung delta U mo. Yung problem na lang, not kilojoule per kilogram, but only kilojoule, right? Because mag-cancel yung kilogram tsaka kilogram. The only problem will be how about the work. I think we already have solved this one to calculate for the work of this, but let me do this time. No, a rough solution for this one. How do we find the work for this? Since this is just an expansion work, we could just solve work using the formula. Work is equal to the negative integral of P dV. Okay, and in this case, we must be able to express P first, since P will be changing, right? It's 3 bar, but we don't know P2. So it's given by this, like P could be expressed as equal to a constant like K over V to the 1.5, right? So let's put that here. Negative, I'm putting the K since it's a constant. I'll have here dV over, I'm replacing P with K over V to the 1.5. Okay, and then integrate that, taken from, of course, V1 to V2. Since we know V1 and V2, then we'll then be getting there negative K V to the what? Negative 0.5 over, so I'm integrating dV over V to the 1.5 over negative 0.5 taken from V1 to V2, and this will lead to 2K Okay, 2k times v2 to the negative zero point 0.5 minus v1. So I'm just really doing the integration of that to the negative zero point 0.5. So v2 is known, zero point 0.2, and v1 is known also, it's zero point 0.2, zero point 0.1, and the only problem will be k. And how do we evaluate k? Well, since this k a constant, we can simply use p1, okay, v1 to the 1.5, it's equal to that constant, okay? And since we know p1 and v1, or actually you could use p2 and v2, but you don't know p2, so we cannot use that. So here, p1, just know that we must put everything in standard SI unit. Like for pressure, if it's bar given, we must convert that first to Pascal, okay? So convert mo yung pressure ng bar to Pascal, yung volume convert mo rin ng, I think it's already okay, m cube. M cube is okay. And then that, so raise mo lang to the 1.5 and then multiply mo to this, you will be getting, supposed to be getting, so I have already solved in the last problem, 17.6, negative 17.6, okay? Meaning nun, work is being done by the system towards the surrounding. This is in kilojoule. Okay. And therefore, from here, minus work. Work is already negative 17.6. So minus negative 17.6 will then be a value equal to like 18.4 and 17.6. So we'll be getting a value of 0.8. Okay, that's negative zero point 0.8 kilojoule. What do you mean by this? Meaning heat is being released to the system during the process of the expansion. The gas releases heat to the surrounding. So that's why the heat transfer is negative zero point 0.8 kilojoule. Negative means heat coming from the system is released towards the surrounding. Thank you.